Alright, in this video we're looking at kinematics, which is pretty much how objects move around. And we just do it in one dimension. Basically, if they're going left it's negative and right would be positive, or if we're moving up, down, up is positive, down is negative. Alright, so we're going to start off with this. So this is a long question, but it's pretty much all that I can really ask you on kinematics. So find v of t and a of t. So we're going to start with our displacement function, which is given up here, and that tells us where the thing is. So that's t cubed take 12t squared plus 21t plus 54, just like that. Now, if we want to find velocity and acceleration, basically to get velocity, we just do the derivative of displacement. And then to get acceleration, we just do that again. So v of t is going to be the derivative. So that's 3t squared take 24t plus 21. A is going to be the derivative again, 6t take 24. Just like that. Now, if you want units, this would be in meters, meters per second, and meters per second. But we don't normally give units when we're just stating the functions like this. All right, find and describe the initial conditions. So the word initial means at the start, or really specifically, t equals 0. So we need s of 0. Now this is going to be, if we plug into s of t, 0 cubed, take 12 lots of 0 squared, plus 21 lots of 0, plus 54, which just simplifies down to 54. And we're going to put meters on there, because we're measuring in meters for this question. V of 0. So it's going to be 3 lots of 0 squared, just using this v function here. Take 24 lots of 0 plus 21, or in other words, that is just 21 meters per second. And then a of 0 is going to be 6 lots of 0 take 24. So in other words, that is minus 24 meters per second. So we can interpret these three pieces, and you do have to say a sentence when you get a question like this. So we could say that the particle is starting 54 meters to the right, origin, traveling at 21 meters per second, right, accelerating 24 meters per second to the left. In other words, it'll be slowing down. If it was moving right and then it's getting pulled back by the acceleration, it will be slowing down. That's how we interpret that. Describe what is happening at t equals 3. So it's pretty much going to be the same calculations here. We're just doing it with 3 rather than 0. So what we want is s of 3, we want v of 3, and we want a of 3. Now it's going to take you ages to do this calculation. So for all kinematics questions, I would suggest that you graph it. What I've done is just graphed s of t here, except instead of t's, I'm using x's. All right, so I've got that in equation, just in that graphing menu there. I'm going to hit draw, and our window is completely wrong. So I'm missing the tops and the bottoms of it, so I might expand my y out. Also, really importantly, time starts at 0 in kinematics problems. Never have negative x values. And let's go up to 15, just to keep it interesting. Y can go from maybe minus 30 to 30, and we'll see if that can help. So let's see what our window looks like. We're still missing quite a bit of it. So maybe let's go from minus 60 to 60. We'll see if that works. Still missing a little bit of it off the top there. So maybe I'll make my max Y value up to 80. We'll see if that is good. Yes, it is. So just to confirm, if I go trace at 0, you can see that that is 54 for the y value, which was my starting position, and 21 was my starting velocity. That's dy dx. Now, if you don't have dy dx shown on the calculator, you go shift setup and turn derivative on. All right, you can't get acceleration from your calculator, but that's what it would be. Yeah, we can use that same process. So trace and then type 3 for this next question. What's happening at 3 seconds? So we can see that y is 36. So that's 36 meters. The velocity at 3 is minus 24. That's my dy dx value, meters per second. An acceleration at 3, we will actually have to plug it in. So 6 lots of 3 take 24 which is 18, take 24, which is -6. Now, this one also asks you to calculate the speed. Now, had I done it in this one, the speed is 21 meters per second. It matches the velocity. If I do it in this one, the speed is 24 meters per second without the negative sign. So if you want a formula for that, speed is just what we call the absolute value of velocity. So you throw out the negative sign essentially. Okay, so we can basically describe what's happening here. So at t equals 3 seconds, particle is 36 meters to the right of the origin, moving left at 24 meters per second, and accelerating to the left at 6 meters per second In other words, it is speeding up because it's moving left and it's accelerating to the left. The velocity and the acceleration are pointing the same way, so it's speeding up. All right, if you want unit stuff, you can write the acceleration units in any of those 3 ways there. I've just been going with that middle option for now, but they all mean the same thing. All right, next, draw sign diagrams of S, B, and A. So this is going to be much like drawing sign diagrams of F, F dash, and F double dash. In fact, we can just think of it like that. So what we're going to do though is, really importantly, we have to start at 0. Time does not go negative in kinematics problems. And what we do for these sign diagrams is we actually put the x-intercepts on. So I'm just going to do this one fairly quickly. The x-intercepts are 4.372, we'll spot that one there. And then the other x-intercept across here is at 9. So that's s of t. And then you use whether it's above or below the axis. So it's above, below, above. Now, if I did extend out my x view to the left, you can see that there would be another x-intercept back there, but we don't include that because we start at 0. So let's put that back. All right, next we got to do our velocity sign diagrams. So with velocity, just remember you put stationary points on there. Now, you absolutely can solve velocity equals 0 and do it algebraically. That would be solving a quadratic there, but we got the graph anyway. We could polysolve it, or we could just find the max and the min. So max there is at 1, so I'm just going to pop that in at 1. And Shift G solve, the min is at 7. So we'll just pop that in at 7. Notice that I'm being very careful to align my sign diagrams. So 7 does fall in between 4 and 9 there. All right, then we use our slope. So it goes up, down, up, just like that. And we put 0 there. All right, next, acceleration. Now, you can't really find points of inflection on the calculator, but we do expect 1 to be there. It's actually a bit hard to tell before or after that intercept. But the acceleration function was back up here. So it was 6t take 24. We're trying to solve that equals 0. 6t equals 24. So t has to be 24 over 6, or in other words, that's 4. So it happens just a smidge before the x-intercept at 4. And notice I'm being really careful to align that 4 just before the 4.372. Now we use the concave, so it's a sad base shape that's negative before it and positive after it. There we go. All right, when and where does the particle turn around? So the turning points are appropriately named because they're the points where it turns around. T equals 1 is one of our turning points, and we got it just from there. And t equals 7. Now, the particle at t equals 1, so I might just go trace and type 1, is at 64. So S of 1 is 64 meters. And if we look at 7, so shift trace, and then we'll type 7, it appears to be at minus 44. So S of 7 equals minus 44 meters. And if you want to give that an interpretation, you can say something like that sentence. 1 second when it's 64 meters right, and 7 seconds when it's 44 meters left. Find the times when the particle's speed is increasing and decreasing. So basically, if we're looking at V and A, and we want to know what the speed is doing, speed. So the speed will be increasing if these are both plus or both minus. But the speed will be decreasing if they're different. And you can think of it like this, like if I'm moving right and being pulled right, that would be both the pluses, then I would be speeding up. But if I would be moving right but being pulled left, I'd be slowing down. So where's the speed increasing and decreasing? As sign diagrams up, we can see that from 0 all the way through to 1, we've got plus and then minus. So that's opposites, so we're decreasing. So speed is decreasing for t between 0 and 1. Then what's happening after 1? So let's have a look at velocity and acceleration. They're both minuses in this range between 1 and 4. So it's increasing from t goes from 1 to 4. All right, what's happening after 4? So it's minus and plus, so that's opposites. So between 4 and 7, and then this one here, both pluses after 7. So there we go, both pluses there. So it would be increasing again for t greater than 7. Now you can sort of see that the graph is getting steeper after 1. Getting steeper means that it's increasing. Getting less steep means that it's decreasing. All right, now this next little section, the velocity, is going to be a bit different. Be really careful about the wording here because they mean very different things. Velocity is increasing means that the velocity is getting bigger. So we already saw that the velocity at the start was 21, and I got that just by tracing at 0. And then let's have a look at x equals like 0.5. My velocity is the dy dx value, that's 9. So it looks to have got smaller than 21 where it started. So that original range, it must have been decreasing a bit. Essentially, you can just look at the acceleration sign diagram. So it's decreasing up till 4, and then it's increasing after 4. So that's what's happening there with the velocity. So decreasing between 0 and 4. Increasing for t greater than 4. Last off, we need to draw a motion diagram. Now these look like sign diagrams, but they are very different. You've got to label them with s of t rather than t. So the numbers on this scale actually mean the position. Now let's look at where it starts. So if I just trace at 0, it's going to start at 54 and it's going to sort of sweep back and forward. I'll put 0 right in the middle. I'm going to put 54 here. All right. And we're starting there. We then went right for a little bit. So if we look at this, basically trace, no, trace is a bad choice there. Let's go maximum. After 1 second, we were at 64. So let's have a look at 64. And you can go through and scale this all up properly, but I'm just going to draw in the key values there for now, 54 and 64. And it turns around. And I'm going to label these points with time, so that's t equals 0, and that is t equals 1. Then after it turns around, it's going to go left for ages until it hits that minimum. So if we go g solve min, after 7 seconds it's at minus 44. So I'm just going to put that there. And then we're going to go all the way back to minus 44 and turn around. And basically after we turn around back to the right, the particle keeps going right forever. And we'll just label this point with a time here as well, t equals 7. So basically the way that by the way, it should not angle up. I'm just bad at drawing. It should be flat. Basically the way that we deal with this is it sort of looks like the graph if you flip your head to the side and also cross your eyes so that it goes mirror imaged. That's what a motion diagram looks like. But this is the actual left-right motion that the particle is taking.